Hello everybody! This video is about the double slit experiment. And maybe you wonder why somebody wants to make yet another video about a more than 200 years old experiment. Especially with already tons of videos on YouTube regarding the subject. Well, for one, most videos don't show you the experiment, but just show you people talking about it. But in this video, we'll have a look at the real deal. And because I show you my own version of the experiment, there is a good chance that you will see aspects of it that you have never seen before. So in the first half of this video, I'll discuss the experiment and the results, and in the second half, I will discuss the quantum mechanics behind it. My version of the experiment uses slits that have a width in the order of only a few wavelengths of light, which is actually significantly narrower than used in most experiments. And we will study diffraction under a microscope instead of at a large distance on a screen. Now, this allows us to look at a few aspects of the experiment with much greater detail. So to perform the experiment, I made various slits ranging from 2.5 to about 25 microns. And in the experiments I also varied the distance between the slits. So let me first show you what you actually see in the experiment, and after that let's have a look at how the experiment works and how the images were made. Here we're looking at the cross-section of a laser beam showing the intensity distribution. And this beam is sent through two very narrow slits of approximately 3.5 microns wide. And this is what you observe after the light has passed the slits. It spreads out in these bright and dark bands, especially in the direction perpendicular to the slit. By the way, notice how the individual slits are not spreading the light as a uniform bump, and this is because of the scale at which we're observing. Basically, everything you see here happens within 1 cubic millimeter. You can see that the pattern of the individual slits already contain a lot of interference structure before the light starts to visually interfere with that of the other slit. As we move further away, the light of the two slits gradually starts to interact. Here at the bottom you see an intensity profile plotted, and this graph shows you the sum of intensities of the pixel columns in a part of the image above the graph. Now notice how the interference pattern develops between the slits. First here in the center, and later it spreads out over almost the complete extent of the pattern. You can actually measure that the interference pattern is quite different from the patterns you would get if you would just add up the intensities of the individual slits. What I show you here is all experimental and not just some simulation. And I wanted to show you this first to demonstrate that the double slit experiment actually contains way more fascinating details than are normally presented. In fact, even the single slit experiment is already pretty groovy by itself. And you don't need fancy equipment to see these things for yourself. You just need a $2 laser diode, a small lens, double slit and simple microscope and a webcam. Now, the way I visualize the intensity evolution is by making use of the very shallow depth of focus that some microscope objectives have. So everything outside a very thin slice of space is out of focus and will reach the CCD sensor as a diffuse and dim blur. And in this way, the images display mainly what's going on in the focal plane and ignore almost everything outside it. Now, as I just showed you, a single slit also displays interference. And that is because even a slit of 3.5 microns wide is still about 6 wavelengths wide. And contrary to interference between slits, it's not easy to assign this interference to a specific location within the slit. But I guess the interference is originating from the fact that the slits are so very narrow that they only allow specific wave modes to exist within the confinement of the slit. Here you can see what happens if the light passes a wedge-shaped slit, ranging in width from about 2.5 microns here to about 25 microns here. Now, at the higher widths you can observe this low frequency component superimposed on the interference pattern. And I guess these are sort of interference phenomena between the different wave modes that can exist within the slit. Diffraction can either be described in the classical way by the Huygens principle of wave diffraction, or with quantum mechanics by the Heisenberg uncertainty principle. Now, since later in this video I'll discuss the quantum character of light, I will focus on the explanation of diffraction as depicted by Heisenberg. The Heisenberg uncertainty principle states that the position of an object and its momentum cannot be independently determined with a very high precision at the same time. And that is the case for all objects, either large or small. In essence, the product of the uncertainties in these properties should always be bigger than the value of this particular constant, which, by the way, has a very small value. Now, the thing is that when you're trying to get information about the position of an object with increasing precision, the uncertainty about its momentum must get bigger. And this phenomenon can best be observed in small objects like elementary particles and light quanta. Now, in the case of light going through a very narrow slit, and especially near the boundaries of the slit, the increased certainty about the position means that the uncertainty in momentum will go up. And for light it means generally that it will spread out. The way I made these slits is by etching the patterns into a thin chromium layer, and I used old lithographic photomasks for this purpose. Now, to etch the patterns I used a photoresist layer and exposed this layer with UV light in the pattern of the slits. After that, the photoresist was developed and the chromium underneath was etched in the desired pattern. Now, the result is tiny transparent slits in the chromium layer. By the way, the exposure patterns in the photoresist were produced by using the do-it-yourself maskless wafer stepper that featured in several of my previous videos. And here's the measurement setup. For the experiments I actually used two different lasers, a green laser diode and a red helium neon laser. They both worked fine, however, generally the beam quality of the helium neon laser was a bit better. So when using the green laser, light was collimated with a small lens and then projected on the slits, which were etched in this disc placed on the table of the microscope. Now, in the case of the helium neon laser, I just used a beam splitter to direct the beam upwards towards the slit. On the other side of the slits is the microscope that can be moved from and to the slit pattern, and the objective of the microscope projects the light on the CMOS chip of a camera, which sends the images to a PC. It may not look that way, but in a monochromatic beam of light, such as the one generated by these lasers, the energy contained in the beam can only have very specific values. In other words, the energy is quantized, and if you increase the intensity of the beam, this can only be done in discrete steps, a bit like going up or down a ladder. These steps are actually extremely small, and in practice you will only notice that light is quantized if you go to extremely low intensity levels. In that case you can get to a point where only a few or even just one of these quanta is present in the beam. So at that point the beam contains only one individual package of energy called a photon. And basically it has no way of interacting with others since it's alone in the beam during its very brief existence. But the thing is, even at these very low intensity levels, we still observe interference. So next I will show you the single photon experiment. In the current configuration I did not need fancy equipment like photomultipliers and pulse counters. I just needed a few gray filters to bring down the intensity of the beam to below single photon level. And to do this, it's not necessary to collect like one photon every second or so. You can collect many millions of photons per second, as is shown in this calculation. I won't discuss it in detail, just pause the video if you want to take a closer look at the calculation. But the bottom line is that you can calculate the photon flux corresponding to, on average, one photon in the beam at any time. And for that you use the travel time of the photon between the slits and the CMOS sensor, which is 0.6 nanoseconds. Now, as you can see, the flux is pretty substantial, about 1.6 billion photons per second. But because of statistics, we have to get significantly below that value to be sure that the majority of all photons is actually alone in the beam. On the other hand, we can use the laser power and the photon energy to calculate the photon flux generated by the laser, both before and after the slits. And from this we can calculate what optical filter is required to get the intensity level of the laser beam significantly below the single photon level. Now for the current helium-neon laser, we can calculate that we have to use a gray filter with an optical density of at least 2, meaning 1% transmission, to get below the 1 photon limit. So if we use an optical density filter of 3, we have on average only 0.09 photon in the beam according to the calculation. But just to be safe, I went all the way down to filters with an optical density of 6. So I dimmed the laser power by a factor of 1,000,000. And this brings down the average photon presence in the beam to 1 in 10,000. And it turns out that this type of single photon flux is easily seen by a standard camera in the current configuration. Now I should add a few remarks to that. The camera I use allows shutter times of 15 seconds, and it is possible to increase the sensor gain significantly. With the higher gain, however, I got a lot of thermal noise in my images. So what I did was cool the camera to about -5 degrees Celsius using a Peltier element, and this suppressed any noise significantly. To demonstrate single photon interference, I took one detail of the interference pattern and collected the data at beam intensity levels ranging over 6 orders of magnitude. And here you see the results that were acquired using different gray filters and of course different shutter times and gain settings. And the result is actually amazingly clear. So whether photons are alone in the beam or whether there are many at the same time, the result of all these interference measurements is exactly the same. So this indeed proves that a photon does not need the presence of another photon to display interference. So the conclusion must be photons somehow interfere with themselves. And the most logical explanation for this would be that each photon is going through both slits at the same time, which is pretty weird. Even with wave properties, it's kind of hard to imagine how a particle-like entity would simultaneously go through 2 slits that are several hundreds of microns apart. But a possible explanation can be provided by using the theory of quantum mechanics. Now, I'm not an expert, but I've given it careful thought. So let me try to explain it the best way I can. But before I can focus on this particular experiment, I must discuss one of the key features of quantum mechanics, which is the intrinsic uncertainties that are present in all matter and light. Basically, these are governed by the Heisenberg uncertainty principle that we have discussed earlier. So let's take, for example, a very small particle with a little mass like an electron. In the classical depiction, it has a very well-defined point-like position at the center of its mass. But in quantum mechanics, the position of a particle is defined by a so-called wave function that can be used to describe the probability of finding the electron at a specific location in space. Now this spatial probability function could, for example, look something like this, where the dark colors indicate a higher probability to detect it. And this does not mean that the electron is moving around extremely fast in a cloud or something. The probability function is, by definition, the position of the particle. And whenever we do an experiment to locate the particle, it can basically be observed anywhere within the distribution. And every experiment we do might just as well have had a different outcome within this set of probabilities. A photon is actually quite different from an electron in the sense that a photon is not bound to a center of mass because it doesn't have any. It's just defined by its momentum or energy or wavelength, and it can't just sit around in one approximate location. In order for it to exist, it must always travel at the speed of light. And this makes the probability distribution of a photon much more elusive than that of a particle. But according to quantum theory, the spatial probability function still is the superposition of all possible locations you might observe the photon. So the question is, what does this probability function look like? Now, in trying to understand this myself, I formulated it as follows. The spatial probability function of a photon will propagate to wherever it's allowed by the physical geometry around it. Put simply, the photon will go everywhere at the same time, as long as the world around it allows it to go there. So let me try to explain this concept visually. Let's say we create a photon right here by spontaneous emission. Now, in spontaneous emission, an atom falls from a higher to a lower energy state, which is an extremely localized process. According to Heisenberg, if you create a photon in such a tiny volume, its momentum will be utterly undefined. And this means that after its creation the photon could go in all directions equally. And it actually does so, with the speed of light. So as long as there's nothing hindering the progression of the photon, its position will be defined by a probability function which will look like the surface of a sphere expanding from the point of creation. And this probability is depicted here as this green ring. Now for simplicity, the depiction is done in 2D, but of course the probability function progresses in 3D space, not just in one plane. So at time t1, the probability function is here, and a little later at t2 it has moved on to here. And since there's no telling in which angular direction it went until we detect it somewhere, the probability of detecting it is equal for all angles on this ring. So this is schematically plotted here in the graph. Now, if we place a set of detectors around this event, one of the detectors might actually pick up on the photon and give us a signal. But does that prove the photon chose a specific path and actually traveled along a line from the point of creation to this detector? Well, not according to quantum theory. It merely proves that at that particular location we had a probability of finding it there, and the fact that we did was just one of many different possible outcomes of the experiment. It could well have been picked up by any of the other detectors with equal probability. Anyway, after we have detected this particular photon, the probability function suddenly becomes irrelevant because at that point the chance of another outcome has suddenly become zero. Basically, you can detect every photon only once, and by detecting it, you destroyed the probability function and eliminated all other possible outcomes of the experiment. Now that concept is one of the most difficult things for us humans to grasp, because in our physical world, things don't travel in all directions at the same time. Like soccer balls, they don't go through both goals at the same time. And in principle, the probability function can cover half the universe if the photon is allowed to travel a long time before it is absorbed. And this is one of the aspects of quantum mechanics where the human reference frame just fails to understand the nature of the photon. From the perspective of the photon, as described by quantum mechanics, there is actually no such thing as a physical distance between the different possible states, simply because the position is, by definition, the superposition of all possible states. And in a sense, quantum mechanics is not meant to make us understand the true nature of light and matter. It's just conceived to explain our observations and measurements. But what we can do is manipulate the probability function of a photon by shaping its physical world. For example, if we place a black screen here, the probability of the photon being behind the screen suddenly becomes very low. In fact, not completely zero, because we still have diffraction occurring at the edges of the screen. Now another way to shape the probability is by replacing the black screen with a mirror. So at some point, part of the probability function travels back in the opposite direction, meaning that you have a higher probability to detect the photon to the right in this image, because the probability function passes the detector twice. There is actually many ways for us to manipulate the probability function of a photon, not just by introducing absorption, diffraction and reflection. Other tools that you can use are, for example, refraction, by using a lens or by using a polarizer. And we can even introduce stimulated emission, where each photon copies the spatial probability function of another photon. So in a laser, for example, we can create a very narrow probability distribution of photons that make it out of the optical cavity. And to get back to the double slit experiment, we can also manipulate the probability function by presenting two narrow slits to a photon. So in many instances, the photon won't make it through because these slits are very narrow, right? So the probability of absorption or reflection by the mask is much higher than a photon actually making it through. But for those who do, this is what the probability function looks like right after the slits. Now, even though this figure suggests that the photon has two options and it has to make a choice for one particular slit, this is actually not the case. Within the current framework, these are just two arms of the same probability function. Now, of course, you can try to assign a specific part of the function to a particular slit. But what does that even mean? Well, it only means the outcome of the experiment got limited to half of the possible outcomes. So let me illustrate this by using this figure. It shows the progression of the probability function in space after passing the slits. Now, by measuring in this area, we can establish the value of the probability function for about half the photons. And the same in this region. Now, if you detect a photon in either of these regions, you might attribute that to a specific path that was chosen by the photon. But once you do that, it can never be observed in one of the other regions, because you can only detect it once. Hence, in this case, we cannot observe interference. On the other hand, if we observe interference, which is only possible in the mixed probability region, we can never assign this to a particular slit, simply because the mixed probability can only exist as the sum of two individual probability functions. And I think this is a nice illustration of why we can never observe interference and establish which path at the same time. The bottom line of my argument is that the probability function of each individual photon will travel along every path available simultaneously. So if you present it with two slits, it will take both at the same time. And in case you're still in disbelief, let's confront the photon with this linear zone plate containing 44 slits. Now, this type of plate creates a very sharp focal line, or in our current context, a very high probability to detect photons here. Now, in the classical depiction, we need the contributions of all slits to achieve this. So, what do you think happens if we send an individual photon through this pattern? After all this, you might have questions or remarks. So if you would like to share them with me, go to the comment section and let me know.